In this video, we are going to derive the Riemann's formula. That is nothing but the product of gamma function and Riemann's zeta function. That is, gamma of s times zeta of s is equal to an integral from 0 to infinity x to the s minus 1 divided by e to the x minus 1. The integral is with respect to x, and real part of s should be greater than 1. And this is the conversion condition for this integral. So let's start the proof. So we start the proof by taking the Euler's integral definition of gamma function. In the integral definition of gamma function, that is gamma of s is equal to an integral from 0 to infinity t to the s minus 1 times e to the minus t dt, where real part of s is greater than 0. Again, this is our conversion condition for the Euler's definition of gamma function. Okay, so now in this Euler's integral definition of gamma function, we substitute t is equal to nx, which implies dt is equal to n dx. So whenever t appears in Euler's definition of gamma function, we substitute nx. So in this way, in equation 2, we see that the n to the s is separated or extracted out from the integral. We have n to the s times the integral from 0 to infinity x to the s minus 1 times e to the minus nx dx. And the thing that should be noted here is n to the s. And this n to the s, that comes or appears in the definition of Riemann zeta function, defined for real part of s greater than 1. You will come to know what actually that is. So actually we made n to the s come out of the gamma integral so that we take it to the left side. We take it to the left side, that is on LHS, and sum it from n is equal to 1 to infinity, both sides. So when I take n to the s to the LHS, it goes into the denominator, and both sides we sum from n is equal to 1 to infinity. And on the RHS side, that sum goes inside the integral, and we have inside the integral an infinite geometric series. The infinite series in RHS of above inside the integral is infinite geometric series starting from n is equal to 1. This is the thing that you have to notice. That particular infinite geometric series is starting from n is equal to 1. We know that for common ratio r, which is less than 1, the infinite geometric series converges to s, which is equal to r divided by 1 minus r, where r is the common ratio, right? So in our case, in RHS of equation 3, that is here, we have the common ratio r is equal to e to the minus x. And hence, by using equation 4, that particular sum or the series infinite sum can be calculated. That is nothing but 1 divided by e to the x minus 1. We put e to the minus x in place of 4 in equation 4, and we factor out e to the minus x in the denominator. And e to the minus x, e to the minus x get cancelled. What remains is 1 over e to the minus x minus 1. Now, next, in the LHS of equation 3, that infinite sum of 1 over n to the s over n that goes from 1 to infinity is just Riemann zeta function defined for real part of s greater than 1. That's the thing, that's the reason we have put t is equal to nx in the gamma integral, so that we can sum it and so that we can get on LHS the product of gamma function and Riemann Zeta function. Substituting equation 5, that is the infinite sum, and the equation 6, which is nothing but the Riemann Zeta function, together in equation 3, we will have our theorem proved. Since the definition of Riemann Zeta function here as summation that goes from n is equal to 1 to infinity 1 over n to the s is only defined for real part of s greater than 1, hence the whole convergence of this integral is defined for real part of s greater than 1. Because LHS and RHS should be consistent, that's why the real part of s should be greater than 1 as a convergent condition for the integral.